In this chapter, we're going to dive into a fascinating and, often overlooked part of application security, logic flaws. Now, these aren't your typical coding bugs. Instead, they're vulnerabilities that are rooted in the very business logic of an application. We hear all the time about these incredibly sophisticated cyber attacks that exploit really complex coding errors. But what if the biggest security risks don't come from that technical complexity at all, but from really simple, flawed assumptions that were made way back in the design phase? We're talking about mistakes hiding in plain sight. So unlike those well-known vulnerabilities, things like SQL injection or cross-site scripting, logic flaws are just different. See, the headline vulnerabilities, they have a recognizable pattern, a signature that automated tools can scan for. But logic flaws, they're totally unique to each application's business process. And that uniqueness makes them pretty much invisible to most automated security scanners, which means you need a much more creative, human way of thinking to find them. So here's how we're going to break this all down. First, we'll get a solid definition of what logic flaws are and dig into their root cause. Then we'll look at 3 really interesting real-world case studies to see exactly how they work. And finally, we'll wrap up by talking about the best ways to actually prevent these things from happening in the first place. All right, let's get right into it. What exactly are we talking about when we say logic flaw? At its core, a logic flaw is when an application's code is technically perfect. It doesn't crash, it doesn't throw any errors, but it can still be manipulated to do something it was never meant to do. Think of it like this. Imagine a secure door with a perfect, unbreakable lock, but the wall right next to that door is made of cardboard. The lock works just fine, but the overall security is shot because of a flaw in the design. That's a logic flaw. It's a loophole in the way things are supposed to happen. What's really crucial to understand is that the defining feature of these vulnerabilities isn't some specific line of buggy code you can just go in and patch. Nope. It's a flawed assumption. It's a particular mindset that overlooks all the weird and unexpected ways a real person might interact with the system. This quote just hits the nail on the head. A developer designs a system with a specific path in mind, right? They're thinking, okay, if a user adds an item to their cart, then they'll go to the payment page, so I'll process the order. It's a very logical, linear process. But they often forget to ask that critical question, but what if? What if the user tries to jump straight from the cart to the shipping confirmation, completely skipping the payment step? Let's make this a lot more concrete with our first case study. This is a classic example of a logic flaw found in an online retailer's checkout process. So, as you'd expect, the application was designed to guide a user through these 4 steps in a very strict order. You browse, you finalize your cart, you pay, and then you enter your delivery info. Seems totally logical and secure, right? And right there, that was the developer's critical mistake. They just assumed that because the website's interface, all the buttons and links, pushes the user along this path, then the user has no choice but to follow it. They completely forgot that a savvy user can control every single request their browser sends to the server. So, how did the attacker pull this off? It's almost shockingly simple. They followed the process right up to step 2, but then instead of clicking proceed to payment, they just manually changed the URL in their browser to the page for step 4, the delivery information page. The application's logic never bothered to check if the payment step had actually been completed, and as a result, it happily processed the order for delivery without ever getting paid. Okay, our next case study shows how an application can make a really dangerous security decision based not on data that's there, but on data that's missing. This one comes from a financial services application. So this application had 2 different ways to change a password. A regular user had to provide their username and their existing password to set a new one, for security. An administrator, however, could reset anyone's password without knowing the old one. But here's the kicker. Both of these functions were handled by the exact same script on the backend. The code's logic was dangerously simple. It just checked if a parameter called existing password was submitted. If it was there, the code figured it was a regular user. If it was missing, the code just assumed, oh, this must be an administrator. You can probably see where this is going. The attack was incredibly easy. An attacker, logged in as just a normal user, uses a simple browser tool to intercept their own password change request. Then, they just delete the existing password parameter from that request. The server gets this modified request, sees the parameter is missing, and is completely tricked into thinking it's an admin, giving the attacker the power to change anyone's password.
All right, this last case study comes from an enterprise application, and it shows how even a simple math check, something designed specifically to prevent fraud, can be completely bypassed by some unexpected input. The application had a pretty important security control built in. To prevent fraud, any funds transfer over $10,000 needed a senior manager's approval. Anything at or below that amount could go through automatically. Standard stuff. The code for this check was super straightforward. If the amount is less than or equal to $10,000, it's approved. Seemed foolproof. But the developers made a huge assumption. They never even considered that someone might try to transfer an amount that wasn't a positive number. Now, this is where it gets really clever. An attacker wants to move $20,000 from account A to account B. So what do? They initiate a transfer of negative $20,000 from account B to account A. And from a pure math perspective, negative $20,000 is definitely less than positive $10,000. So the security check passes. No manager approval needed. And here's the final, crucial part of the flaw. A completely separate part of the application, the banking module that actually processes the transfer, interpreted a negative transfer from B to A as a positive transfer from A to B. And just like that, the attacker successfully moved $20,000, completely bypassing the anti-fraud control, all because of a simple, flawed assumption about numbers. So, now that we've seen how these things work in the real world, we get to the most important question of all. How do we stop them? How can we actually build applications that are tough against these kinds of attacks? Well, preventing logic flaws isn't about buying some new security tool or writing one perfect line of code. It really requires a fundamental shift in how you think during the entire development process. Developers have to stop thinking only about the happy path, the way users are supposed to behave, and start thinking like an attacker who is actively trying to break the system's logic. The key is to challenge every single assumption you make. That means you need to adopt a few defensive strategies. First, write down every design assumption explicitly. Things like, a user must complete payment before shipping. Second, actively look for ways a user could behave unexpectedly. Third, never ever trust that data will arrive in the right order, or even that it will arrive at all. And finally, you have to be super strict about validating all user inputs. If an amount should be positive, your code must explicitly reject negative numbers.
Ultimately, if there's one thing you take away from this, it should be this. The most robust security doesn't come from some fancy algorithm or an expensive firewall. It comes from a mindset of healthy skepticism. It's about constantly challenging the design and asking that one critical question at every single stage. But what if? What if a user does something we don't expect? That question, that's the real foundation of a secure application.